So AC circuit recap. All right, so what I've discovered is that I need to do these in really small bits. All right, so I have a AC circuit, or AC power supply. So that's the symbol for an AC power supply. We hooked it up to a resistor. And from this, we came out with the fact that for a resistor, the current and the voltage are in phase, which means that when I do my phasor diagram, the voltage going across the resistor and the current going through the resistor, those phasors will be right on top of each other. Also pointing out, as part of the recap, is that we're using a lowercase I and V here, and this represents the instantaneous value. Instantaneous value. And if I ever use a capital I or a capital V, let's for instance, I should put a subscript R there, this would represent the amplitude or maximum value. And so then we did the capacitor. And if you recall, the Iceman, that for a capacitor, the current leads the voltage by 90 degrees, or pi over 2 if you're dealing with radians. And that's what this right here is indicating, the fact that if I have a capacitor, we have I before E, and the E comes from the fact that oftentimes voltage is dealt with in terms of EMF, and it really should be an epsilon, but if you do electrical engineering, they use a capital E instead of the EMF because, well, that convention was established back before fonts were easy. And then we did the inductor. Eli comes into play. And so I have a AC power supply, and I have an inductor. And then for inductor, the voltage across the inductor leads the current by 90 degrees, or pi over 2 radians. And so that's what this is indicating right here, is the fact that for an inductor, we have the voltage or the EMF coming before the current. From this set, we also developed a couple other rules here. We had so we know that for a resistor, that the V equals IR, and those are capital letters here that we're talking about. That for a capacitor, so this is voltage across the resistor. For a capacitor, the voltage across the capacitor is equal to I times X sub C, which is this X sub C is the capacitive reactance, and X sub C equals 1 over omega times the capacitance, where omega is the angular frequency. So this is the angular frequency. And that for an inductor, the voltage across the inductor is equal to I times X sub L, where this is the inductive reactance. I'll actually write that out, inductive reactance. And X sub L is equal to omega times L. All right, so those are the recap of that part. And then we went through doing a phasor diagram for slightly more complex circuits. So we dealt with a resistor and a capacitor in series. and introduced the idea of impedance. And I think that's spelled correctly. And the symbol for impedance is Z, and that the EMF, or the magnitude, sometimes put a little zero down here. This is the maximum value of the voltage from the power supply is equal to the current coming out of the power supply times the impedance. And then we did it. The last thing we did was we did the resistor and the capacitor in parallel. I do want to point out that there is not a formula for impedance. There are multiple formulas depending upon the situation. Unlike on the previous screen when we talked about the reactance, there are set formulas for that. However, impedance you have to derive each time. As a matter of fact, a large number of problems deal with actually trying to find the formula for impedance for that situation. So I'm going to end this session and get ready to actually do a more complex circuit.